Alright, so today we're going to go ahead and finish off this handout. We're going to be working kind of the opposite direction we did before. We're going to be given some pieces of information about a graph, and then we're going to graph it. Instructions don't tell us to do this, but we're going to do it anyways because it's going to be very beneficial for us to do so. We're going to determine the exact function that describes the pieces of information we are given. So let's go ahead and start this off with A. We're given this first bit of information. We have a rational equation, and it's got some discontinuities. These discontinuities are at x equals -1, and that is an odd power. The next one is at x equals 2, and that is an even power. So discontinuity. So what is that going to look like? Like, what is an equation that follows those properties? Well, we've got, A is just a random constant. Doesn't matter what you pick. It's just constant. We want to make sure we get these discontinuities. We have x plus 1, which is an odd power. We can leave that at 1 because we want this to be of the lowest possible degree. So we're going to keep everything down low. And x equals 2, which is an even power. And so this will be x minus 2, and we want an even exponent up there. And we're trying to keep these as low as we can. So this would give us discontinuities at -1 and +2. And so let's go ahead and graph those. And to graph those, we simply just do a dotted line here to show that's our asymptote. X equals -1. And then right here at x equals +2. And so we're going to go ahead and examine this with Desmos. Just those discontinuities, the bit of information we have so far. And so we say y equals some constant a over x plus 1, and then x minus 2, and of course the second one is the x minus 2 is an even power. Let's add a slider for a, because keep in mind, a is simply just a arbitrary constant. We can make it whatever we want. Note that everything flips to the other side if a is negative versus positive. Other than that, a is simply a scalar. It scales what a graph looks like in the vertical direction, right? It's a vertical stretch factor. All right, so let's take a look at what's going on at this first discontinuity at x equals -1. Note that is corresponding with this guy right there. All right, so at this discontinuity, note that it changes sides, right? Down low, then up high as we go from one side of the asymptote to the other, right? This is a common feature of any odd discontinuity. I can put any odd power onto this, and we will still see that behavior manifest. All right, so, and also if a is negative, note that property still holds. It's just, instead of going down then up, now we're going up then down, right? Anytime you have an odd discontinuity, you're going to change sides as you go from one side of the discontinuity, one side of the asymptote line to the other. All right, so let's take a look at this one, right? X minus 2, so that's going to be an asymptote at x equals +2, right, because it's always a different sign. And so let's go ahead and look at that spot. So we notice that they're both on the same side, right? This is what happens for any even discontinuity, and if a becomes positive, they're both on the same side, just both up. And this will be true for any even discontinuity, regardless of the power, right? If we go 4, 6, or 8, they all do the same thing. Keep it lowest degree possible, though. And there we go. All right, so back to the handout. All right, so now we've got a dealing with the zeros of this rational polynomial equation. We have a 0 of an even power at x equals -2, then a 0 of an odd power at x equals 0. All right, so just all by itself, this would imply that we've got an equation that looks like this: x plus 2, and it's an even power, so put a 2 there, and then a 0 of an odd power at 0, right? X minus 0, of course we don't need to include that minus 0 part, and so let's write cubed. Note up here when it said odd power, we just left it as a 1. Here we're putting a 3. The reason we're saying a 3 is because when we talk about zeros, they could be linear or they can be odd. So anytime we're talking about a 0 having odd power, it means we're talking about an odd power of 3 or above. And if it's linear, that just means it's a power of 1. All right, so this would be our equation by itself. Of course, this is not all by itself. It has this guy working in tandem with it. So putting these two together, we would have a times x plus 2 squared times x cubed, and then divided by x plus 1 times x minus 2 quantity squared. All right, so let's go ahead and graph these zeros. We have one at -2, putting it right there, and then we had another one at 0. All right, so this 0 at -2, that was an even power, and this one at 0, that was an odd power. All right, so we take notes so that we know what we're doing so we don't lose track. Let's go ahead and take a look at this in the Desmos front. All right, so for real fast, let's ignore what we've done so far. Let's take a look at just the regular zeros. We have y equals a times x minus 2 quantity squared. I'm sorry, not minus 2, plus 2. And then we've got x to the 3rd power. All right. And so you can see we've got a 0 here of an even power. Note that it bounces off of it like a square function does. And then we've got the cubic function where it pauses through the same way a cubic function would as well. And so let's go ahead and plot these zeros. So we've got one at -2 and 0. And then we've got another one here at the origin, 0, 0. All right, so we've got those zeros here. Now, this would be great if this was all we're dealing with. However, these guys are a part of a rational polynomial. And belong right there. So let's go ahead and make that one disappear for the time being. Before we graph the whole thing, I want us to go back to the handout. And look at this last part. We've got a -x squared, right? And so that means we've got our lead term is approaching -x squared, right? Remember, that's the lead term at the top divided by the lead term at the bottom. All right, so since it's -x squared, that means the end behavior is down, down. So let's put it in the graph. So we have down, down like this. And let's go ahead and go through the graph. We've got enough to graph it, and then we're going to come back and figure out what the exact form of this equation is going to be. So because we start off in the down position, we're coming from here, and then we come across this 0 here. It's even, which means it acts like a square near, so it comes back down, and then it hits this asymptote, and so it just follows the asymptote all the way down because it cannot cross the asymptote. If you do your graph and you draw something like this, it's wrong. All right, so now we have this guy right here at x equals -1. -1, that was an odd discontinuity. Let's go ahead and just remind ourselves this one is an odd discontinuity, and this one is an even discontinuity. And so since it's an odd discontinuity, it changes sides. And so it comes through like this. It encounters this 0. What does it do here? Well, we've got a note here that is an odd discontinuity. So it goes through like a cubic function does. And then encounters this discontinuity and travels its way on down. This is an even discontinuity. So it means it stays in the same side. So it comes here. Does it see any zeros along here? No, it does not. So the next thing it encounters is the end behavior, which is back down. So it continues on. At some point, has to turn and head back down. So that is what our graph, a sketch of our graph would look like. No, it's not no y scale to it, only an x scale. Now let's go ahead and figure out what does this function, the form of this function actually take that follows all of these behaviors. So first off, let's calculate the lead term of this guy right here. Right, so lead term of the top over lead term of the bottom, we have a times x squared times x cubed all over x times x squared, where once again this x squared comes from this term here. This x cubed term comes from that guy there. These two terms are linked this way, and where does x squared term come? It comes from that guy right there. Alright, so let's go ahead and simplify this. We have a x squared and x squared right off the top. And so this becomes a times x cubed over x, which is simply x squared. So note the last thing we got to keep in mind. We have an a, and we got a -1. So what does a equal? It equals -1. So the final form of that our equation must take that fit all of these bits of information is simply negative x plus 2, and then everything else is the same. X cubed over x plus 1 times x minus 2 quantity squared, right? So that is what the equation would look like. Let's go to Desmos now and take a look at this graph. So one thing, we have to adjust the a. What does the a equal? A equals -1, as we already covered. So we need to come over here, change that to -1, and note that this now fits exactly what we were predicting. You know, there was no y scale, so the scale is a little bit off, but that's okay, because it's just a sketch. We're just trying to get the idea. Okay, you got to kind of zoom out to see what's going on down here. But everything is acting the way we did. A nice cubic behavior there. We have a square function happening right there. At the right scale, looks very much like a square function. All right, so that's it. That is our function.